The largest structures gravity can hold together are not individual galaxies. They are something far more massive. Thousands of entire galaxies cluster in single regions of space. The space between those galaxies is not empty either. It is filled with material hotter than anything you can imagine. Tonight we are tracing how astronomers discovered these cosmic empires. You will see the observations that revealed invisible matter holding everything together. And you will learn why the hottest material in the universe sits between galaxies instead of inside them. Before we dive into cosmic scale, drop a comment about where you are listening from. If you enjoy these space explorations, consider subscribing. These journeys through the universe are meant to be shared. Astronomers made a discovery that broke the rules. They pointed telescopes at a region of space called the Coma Cluster. What they saw did not make sense. Thousands of galaxies packed into one area, not scattered randomly across space, clustered together like a cosmic city. Those galaxies were moving fast, racing through the cluster at tremendous speeds. Here is the problem. At those speeds, everything should fly apart. The gravity from the galaxies themselves is not strong enough to hold the structure together. Yet the cluster stays perfectly stable. It has been stable for billions of years. Something invisible had to be holding it all together. This became the first direct evidence for dark matter on cosmic scales. That invisible material, what astronomers call dark matter, makes up most of the cluster's mass. Roughly 5 times more dark matter exists than all the visible galaxies combined. Without this hidden framework, those racing galaxies would scatter across space. Instead, an invisible gravitational scaffolding binds thousands of galaxies across millions of light years. Galaxy clusters represent absolute limit of gravitational binding in our universe. Nothing larger stays intact against cosmic expansion. Between those thousands of galaxies sits something most people never imagine. Look at images of galaxy clusters. You see bright dots representing galaxies. The space between them looks empty. It is not empty at all. X-ray telescopes revealed the truth. When astronomers pointed these instruments at galaxy clusters, they detected intense radiation. The spaces between galaxies glow brilliantly in X-rays. Regular optical telescopes completely miss this component because it does not emit visible light. The space contains gas, extremely hot gas. This plasma reaches temperatures exceeding 15 million degrees Celsius. That is hotter than the core of most stars. This heated material makes up more normal matter than all the stars in all the galaxies combined. Think about that. The universe's largest reservoir of ordinary matter floats invisibly between galaxies. You can only detect it with special X-ray instruments orbiting Earth. How does gas reach such extreme temperatures? Gravity does the work. Smaller galaxies grudge to form larger clusters. Matter falls into enormous gravity wells. As it accelerates inward, collisions create shock waves. Those shock waves heat everything to millions of degrees. This blazing ocean fills the space where galaxies live. Astronomers faced a math problem. They counted all the visible matter in galaxy clusters, all the stars in all the galaxies, all the hot gas between them. They added everything up. The numbers did not work. Galaxy clusters contain far more mass than you can see. The visible matter accounts for only a small fraction of the total. Scientists call this invisible component dark matter. The name simply means matter that does not interact with light. Dark matter makes up most of a galaxy cluster's mass. Roughly 5 times more dark matter exists than ordinary matter. This invisible framework creates the gravitational well that holds everything together. Without it, galaxy clusters could not exist. How do astronomers know dark matter exists if they cannot see it? They measure its gravitational effects. Galaxy velocities reveal total mass. The way hot gas distributes shows gravitational strength. Background galaxies get distorted by the cluster's gravity. That is called gravitational lensing. All these measurements point to the same conclusion. An invisible halo surrounds each galaxy cluster. This dark matter halo extends far beyond the visible galaxies. It creates the structure's backbone. The dark matter fell together first, billions of years ago. Then ordinary matter fell into the gravitational wells dark matter created. Dark matter does not just exist alongside visible matter. It fundamentally shapes cosmic architecture. Normal space contains very few galaxies. Point your telescope at a random patch of sky. You might find 1 or 2 galaxies in that volume. Galaxy clusters represent the opposite extreme. The same volume of space in a cluster contains hundreds of galaxies, sometimes over 1,000. This creates a cosmic traffic jam on an unimaginable scale. The density difference is staggering. Galaxy clusters pack galaxies hundreds of times more densely than average space. This crowding creates an entirely different environment. Galaxies constantly pass near each other. Their gravitational fields interact. Sometimes they collide and merge. This dense environment transforms galaxies. A galaxy living in a cluster experiences completely different conditions than one floating in empty space. The hot gas between galaxies creates ram pressure. Imagine sticking your hand out a car window. As galaxies move through this hot medium, the pressure strips gas away from them. Losing gas changes everything for a galaxy. Gas fuels new star formation. Take away the gas and star formation stops. That is why many cluster galaxies appear red and dead. They exhausted their fuel long ago. The dense cluster environment killed their ability to make new stars. Cosmic real estate determines a galaxy's fate. Individual galaxies in a cluster move in seemingly random directions. Some orbit through the cluster at incredible speeds. Others move more slowly. This chaotic motion follows no obvious pattern. Astronomers measure something called velocity dispersion. That is just a technical term for how much galaxy speeds vary within a cluster. High dispersion means galaxies move at wildly different velocities. Galaxy cluster measurements show extreme velocity dispersion. Galaxies race through clusters at speeds exceeding 1,000 kilometers per second. That is roughly 1% the speed of light. At these velocities, individual galaxies cross the entire cluster in less than a billion years. This creates a dynamic equilibrium. Think of it like gas molecules in a container. Each molecule moves randomly, but overall pressure and temperature stay constant. Galaxy clusters work similarly. Individual galaxies zoom around chaotically, but the cluster as a whole maintains stability. The velocity measurements reveal total cluster mass. Higher velocities require more gravity to prevent escape. By measuring how fast galaxies move, astronomers calculate how much total mass holds them in place. This method confirmed that dark matter dominates cluster mass. The galaxies move too fast for visible matter alone to contain them. At the center of most galaxy clusters sits something special. One galaxy vastly outweighs all the others. Astronomers call it the central dominant galaxy. This cosmic monster grew by consuming its neighbors. The central galaxy did not start out so massive. Billions of years ago, began as an ordinary cluster member. But location determined its fate. Sitting at the cluster's gravitational bottom, other galaxies gradually fell toward it. Some galaxies passed too close. Gravity tore them apart. The central galaxy absorbed their stars. Each merger added mass. Over billions of years, countless smaller galaxies contributed material. The central galaxy grew to enormous size. This central giant shapes the entire cluster structure. Its gravity influences how other galaxies move. The hot gas between galaxies responds to its gravitational pull. Even the cluster's overall shape reflects the central galaxy's dominance. Most central dominant galaxies share similar characteristics. They appear as massive elliptical galaxies, egg-shaped collections of old stars. They contain little gas for making new stars. Their stellar populations consist of ancient stars formed billions of years ago. These galaxies represent the endpoint of galactic evolution in dense environments. the biggest fish in the cosmic pond. The hot gas between galaxies does not maintain uniform temperature. Instead, it shows a distinct pattern. Temperature peaks at the cluster center and gradually decreases moving outward. Astronomers measure this temperature profile using X-ray telescopes. Different gas temperatures emit X-rays at different energies. By analyzing the X-ray spectrum, they map temperature across the cluster. The hottest regions reach temperatures exceeding 100 million degrees in some clusters. That is 7 times hotter than the Sun's core. As you move away from the center, temperature drops. The outer edges might only reach a few million degrees, still incredibly hot by any normal standard. This temperature pattern reveals the cluster's gravitational structure. Hotter gas indicates deeper gravitational wells. The center contains the most mass, creating the deepest well. Gas falling into that well heats to extreme temperatures. The temperature profile also shows the cluster's history. Smooth temperature gradients indicate relaxed clusters that have not experienced recent mergers. Disturbed temperature patterns reveal ongoing collisions between galaxy groups. Reading the temperature map tells the cluster's story. The gas remembers every gravitational disturbance. Galaxy clusters contain staggering amounts of mass. Astronomers estimate total cluster mass using several independent methods. Galaxy velocities provide one measurement. Gravitational lensing gives another. Hot gas distribution offers a third approach. All methods agree on the basic scale. A typical large galaxy cluster contains mass equivalent to roughly 1 quadrillion suns. That is a 1 followed by 15 zeros. Some of the most massive clusters exceed this by another factor of 10. Breaking down that mass reveals cluster composition. About 15% consists of ordinary matter in galaxies, stars, planets, gas dust. Another 5% exists as the hot gas filling space between galaxies. The remaining 80% is dark matter. This mass distribution holds crucial cosmological significance. Galaxy clusters represent fair samples of the universe's total matter content. Their composition reflects cosmic averages. The fact that dark matter dominates cluster mass tells us dark matter dominates the universe. Measuring cluster masses also tests fundamental physics. The distribution of cluster masses across cosmic history constrains how fast structure formed. Too many massive clusters early on would contradict our understanding of cosmic expansion. The observed mass distribution matches theoretical predictions remarkably well. Clusters serve as cosmic laboratories for testing the universe's fundamental properties. Galaxy clusters did not form all at once. They built up gradually through cosmic history. Astronomers call this hierarchical structure formation. Small structures formed first. They then merged to create larger structures. The process began with individual galaxies forming billions of years ago. Gravity pulled nearby galaxies together into small groups. These galaxy groups contained just a few dozen members. Over time, multiple groups fell together. As groups merged, they formed galaxy clusters. The mergers released enormous energy. Shock waves heated the gas to millions of degrees. The galaxies themselves mostly passed through each other. Remember, space is mostly empty. But the hot gas collided violently. This hierarchical assembly continues today. Astronomers observe clusters in various stages of merging. Some appear relaxed and symmetric. They have had billions of years to settle into equilibrium. Others show clear signs of ongoing collisions. The largest structures in the universe form from multiple cluster mergers. Astronomers call these superclusters. They span hundreds of millions of light years. Superclusters represent the universe's largest gravitationally influenced structures. Beyond this scale, cosmic expansion dominates over gravity. Hierarchical assembly built the cosmic web we observe today. Galaxy clusters create one of nature's most spectacular optical effects. Their gravity is so strong it bends space itself. Light traveling through that bent space follows curved paths. This effect is called gravitational lensing. Einstein's general relativity predicted it a century ago. Galaxy clusters provide the perfect laboratories for observing it in action. Background galaxies far beyond the cluster appear distorted. Their light passes through the cluster's gravitational field on its way to Earth. The gravity bends those light rays. Instead of seeing the galaxy's true shape, we see a distorted image. Sometimes the distortion creates giant arcs. These bright curved features stretch across cluster images. Each arc is actually a single background galaxy stretched by gravity. The cluster's mass distribution determines the arc's exact shape. Strong lensing can create multiple images of the same bound galaxy. Light takes different curved paths around the cluster. Each path arrives at a slightly different angle. We see the same galaxy in several places simultaneously. Gravitational lensing serves as a powerful scientific tool. The amount of distortion directly measures total cluster mass. This works regardless of whether that mass is visible or dark. Lensing measurements reveal dark matter's presence before any other method. Today, astronomers use lensing to map dark matter distribution with exquisite precision. Gravity's ability to bend light transformed it into the universe's most accurate scale. For most of human history, astronomers studied the universe using visible light. Optical telescopes revealed galaxies, stars, and gas clouds, but they missed the universe's largest structures almost entirely. Everything changed when X-ray astronomy began. The first X-ray telescopes launched into space in the 1960s. They detected radiation invisible to human eyes. When astronomers pointed these instruments at galaxy clusters, they made a stunning discovery. The space between galaxies blazed with X-ray emission. This completely unexpected finding revealed that hot gas filled the voids. The gas temperature, tens of millions of degrees, explained why optical telescopes missed it. Material that hot does not emit visible light. It radiates X-rays instead. This discovery transformed our understanding of galaxy clusters. The hot gas contains more ordinary matter than all the cluster's galaxies combined. It represents the largest reservoir of baryonic matter in bound structures. X-ray observations became essential for studying cluster physics. Modern X-ray telescopes map cluster properties in exquisite detail. They measure temperature distributions. They detect metal enrichment from stellar processes. They reveal shock waves from cluster mergers. Every X-ray observation adds to our understanding of how the universe's largest structures formed and evolved. The invisible became visible, and the universe got much more interesting. Most of a galaxy cluster's volume contains something you can't see with your eyes. It's not empty space. It's not dark matter either. The space between galaxies holds ionized gas. Astronomers call this the intracluster medium. That's just their term for the material filling the gaps between cluster galaxies. This gas exists in a state called plasma. Plasma forms when gas gets so hot that electrons strip away from atoms. The result is a soup of charged particles, free electrons and atomic nuclei floating separately. This represents the fourth state of matter beyond solid, liquid, and gas. The intracluster medium is incredibly thin, far less dense than the best vacuum we can create on Earth. Yet it accounts for most of the cluster's normal matter. More baryonic matter exists in this diffuse plasma than in all the cluster's stars combined. Think about that scale. Every star in every galaxy in the cluster, all their combined mass. The invisible gas between them outweighs it all. This plasma makes galaxy clusters the universe's largest reservoirs of ordinary matter in a single bound structure. The hot plasma between galaxies emits radiation constantly, but not the kind of radiation you can see. The emission happens at X-ray wavelengths, invisible to human eyes. The radiation comes from a specific process. Free electrons zoom through the plasma at tremendous speeds. These fast-moving electrons occasionally pass close to positively charged atomic nuclei. When they do, electromagnetic forces deflect the electron's path. Changing the electron's direction costs energy. That energy gets released as a photon, a particle of light. The faster the electron was moving, the more energetic the photon it creates. In million-degree plasma, electrons move fast enough to produce X-ray photons. Astronomers call this process Bremsstrahlung. The German word literally means breaking radiation. Each electron nucleus encounter acts like a tiny break on the electron's motion. The breaking converts kinetic energy into electromagnetic radiation. This process generates a continuous X-ray spectrum. Unlike emission from atoms that creates specific wavelengths, Bremsstrahlung produces radiation across a broad range of energies. The spectrum's shape directly reveals the plasma's temperature. Hotter plasma means faster electrons. Faster electrons create more energetic X-rays. Reading the spectrum tells you how hot the gas is. X-ray spectra from galaxy clusters show something unexpected. Sharp spikes appear at specific energies. These aren't from the Bremsstrahlung process. They're emission lines from iron atoms. Iron shouldn't exist in significant quantities. Stars create iron through nuclear fusion, but iron formation requires extreme conditions. The cores of massive stars near the end of their lives. When those stars explode as supernova, they scatter newly forged iron into space. The presence of iron in the intracluster medium tells a story. Billions of years of star formation and death enriched this gas. Each supernova added a tiny amount of heavy elements. Over cosmic time, those contributions accumulated. The iron atoms in the plasma aren't neutral. The extreme temperature stripped away most of their electrons. What remains are highly ionized iron atoms. When these ions capture electrons temporarily, they emit X-rays at characteristic energies. Different regions of a cluster show different iron abundances. The central regions typically contain more iron. That makes sense. The central galaxy has been manufacturing and distributing heavy elements for the cluster's entire history. The iron distribution maps the cluster's chemical evolution. Every iron atom in that plasma came from a star that lived and died. The intracluster gas doesn't distribute evenly. Density peaks sharply at the cluster center. Moving outward, density drops rapidly. Astronomers measure this density profile using X-ray observations. The brightness of X-ray emission depends on gas density. Specifically, brightness scales with density squared. Double the density and brightness quadruples. The measured profiles follow a predictable mathematical form. Density decreases exponentially with distance from center. This isn't random. The pattern reflects the cluster's gravitational structure. Gas settles into gravitational wells. Where gravity pulls strongest, gas accumulates most densely. The center contains the deepest part of the gravitational well. Gas density peaks there. Moving outward, gravity weakens. Gas density decreases correspondingly. This creates a beautiful connection. The gas density profile traces the dark matter distribution. Dark matter creates the gravitational wells. Gas responds by filling those wells. Measuring where the gas sits reveals where dark matter must be. The visible gas maps the invisible dark matter halo. Hot gas should cool down over time. As it radiates X-rays, it loses energy. Losing energy means dropping temperature. Cooler gas becomes denser and sinks deeper into the gravitational well. This process should create a steady flow. Gas at the center cools and contracts. Gas from larger radii flows inward to replace it. That replacement gas also cools and contracts. The cycle continues, creating what astronomers call a cooling flow. Here's what should happen. The central gas cools enough to form new stars. Massive amounts of gas, hundreds of solar masses per year, should rain down onto the central galaxy. This would trigger intense star formation. But observations show something different. The expected cooling doesn't occur. Star formation rates fall far below predictions. Something prevents the gas from cooling all the way down. The most likely culprit sits at the central galaxy's core. A supermassive black hole actively feeds on nearby matter. As material spirals into the black hole, it heats surrounding gas through various processes. This heating counteracts the cooling. The system reaches a balance. Gas tries to cool and fall inward, while black hole activity heats and pushes outward. This delicate equilibrium prevents runaway cooling. Galaxy clusters didn't form peacefully. They built up through violent mergers. When smaller galaxy groups collided, their gas crashed together at tremendous speeds. Those collisions created shock waves. Think of a sonic boom, but on cosmic scales. Gas moving faster than the local sound speed generates a shock front. Material crossing that front suddenly compresses and heats. The shock converts gravitational energy into thermal energy. As galaxy groups fell together, gravity accelerated them. That acceleration gave the gas kinetic energy of motion. The shock transformed that kinetic energy into random thermal motion of individual particles. This process heated the intracluster medium to its current temperatures. Most of the heat came from the cluster's initial assembly. Major mergers over billions of years added additional heating. Each collision injected more energy into the gas. The shock heating also explains why the gas is so hot. Gravity wells this deep require tremendous velocities to escape. Gas falling in reaches speeds of thousands of kilometers per second. When that fast-moving gas suddenly stops at a shock front, all that kinetic energy converts to heat. The result is plasma at tens of millions of degrees. The intracluster medium contains weak magnetic fields. These fields measure just a few microgauss in strength. That's roughly 1,000,000 times weaker than a refrigerator magnet. Despite their weakness, these magnetic fields matter. They influence how the plasma behaves. Charged particles spiral around magnetic field lines rather than moving freely. This affects heat transport through the gas. Heat normally flows from hot regions to cool regions through conduction. In ordinary gas, particles carrying energy move freely. In magnetized plasma, particles can't cross field lines easily. They're confined to moving along the field. This dramatically reduces heat conduction perpendicular to field lines. Heat flows freely along field lines, but barely at all across them. The magnetic field creates invisible barriers to heat transport. The fields also affect gas motion. Moving plasma drags magnetic fields along with it. The fields, in turn, resist certain types of motion. This creates complex feedback between gas dynamics and magnetic fields. Astronomers detect these fields through their effect on radio waves. Radio emission from the cluster gets slightly polarized by passing through magnetized plasma. Measuring that polarization reveals field strength and orientation. The magnetic structure adds another layer of complexity to cluster physics. The intracluster medium isn't calm. It churns constantly in turbulent motion. This turbulence mixes material throughout the cluster. Galaxies moving through the cluster create wakes in the gas. Like boats moving through water, they stir up the medium they pass through. These wakes generate turbulent eddies. The eddies cascade down to smaller and smaller scales. Cluster mergers inject enormous amounts of turbulent energy. When galaxy groups collide, they violently disrupt the gas. The collision creates complex, chaotic flows. These flows take billions of years to settle down. Turbulence helps explain several observed features. It can transport heat more efficiently than conduction alone. Turbulent mixing redistributes material, helping homogenize the cluster's composition. It also affects the magnetic field structure, amplifying and tangling field lines. The turbulent motions contain significant energy. This energy eventually dissipates as heat. The turbulent cascade energy flowing from large eddies to small ones provides additional heating to the gas. Turbulence represents a hidden energy reservoir in galaxy clusters, influencing their thermal structure in ways still being understood. The intracluster medium contains more than just hydrogen and helium. It holds significant amounts of heavier elements, what astronomers call metals. These metals didn't exist when the cluster formed. The early universe contained only the lightest elements. Everything heavier came from stars. Nuclear fusion in stellar cores built up carbon, oxygen, silicon, iron, and other elements. Supernovae distributed those elements into space. When massive stars exploded, they scattered newly forged metals across vast distances. Over billions of years, the intracluster medium accumulated this enriched material. The central regions show the highest metal content, roughly 3 times solar metallicity in some cluster cores. That's 3 times more heavy elements than our Sun contains. This enrichment reflects the central galaxy's long history of star formation. Metallicity decreases moving outward from the cluster center. The outer regions contain less enriched material. This gradient tells us where most of the star formation occurred. The central regions dominated metal production. Reading the metallicity distribution reveals the cluster's history. When did most stars form? How efficiently did supernovae distribute metals? How well did turbulence mix everything together? The chemical signatures answer these questions. Every heavy element atom in that plasma came from a star's nuclear furnace. The intracluster gas sits in a state of balance. Gravity pulls it inward. Thermal pressure pushes it outward. These forces exactly cancel. Astronomers call this state hydrostatic equilibrium. It's the same balance that prevents our atmosphere from collapsing or escaping. Pressure gradients support the gas against gravity's pull. This equilibrium allows a powerful calculation. Measure the gas temperature and density profile. From those measurements, you can calculate the total gravitational mass. The pressure needed to support the gas reveals how much gravity must be pulling on it. This method provides one of the most reliable ways to weigh galaxy clusters. It doesn't depend on galaxy motions or lensing measurements. It comes directly from the gas physics. The equilibrium also reveals dark matter's presence. The measured gravitational mass far exceeds the visible matter. Most of that mass must be something we can't see. Dark matter provides the extra gravity holding the hot gas in place. Disturbances break this equilibrium. During cluster mergers, the gas gets shocked and compressed. The system temporarily loses balance. Studying departures from equilibrium reveals ongoing dynamic processes. Perfectly relaxed clusters show beautiful hydrostatic balance. Disturbed clusters show exactly where and how equilibrium breaks down. Astronomers discovered a problem decades ago. They calculated how fast the central gas should cool. The numbers predicted dramatic consequences. The hot gas radiates rays continuously. That radiation carries energy away. Losing energy means the gas should cool down. As it cools, it becomes denser and sinks toward the center. The calculations showed hundreds of solar masses per year should be cooling and falling inward. That much gas accumulating at the center would trigger intense star formation. The central galaxy should be forming stars at spectacular rates. But observations showed something completely different. Star formation rates were far lower than predicted. Some clusters showed almost no star formation despite predictions of vigorous cooling flows. The solution involves the central black hole. Most massive galaxies contain supermassive black holes at their cores. When these black holes actively feed, they release enormous energy. That energy heats the surrounding gas. Jets of energetic particles shoot out from near the black hole. These jets inflate bubbles in the hot gas. The bubbles rise, stirring the medium and depositing energy. This heating counteracts the cooling. The system maintains a delicate balance. Gas tries to cool and fall inward. Black hole activity heats it back up. Too much heating, and the black hole's fuel supply gets cut off. Too little heating, and cooling wins. The balance self-regulates. Feedback between cooling gas and black hole heating creates stability. This solves the cooling flow problem while revealing deep connections between supermassive black holes and their cosmic environments. Astronomers calculated the total mass they could see in galaxy clusters. They counted every star in every galaxy. They measured the hot gas between galaxies. They added everything up. The numbers didn't work. The visible matter couldn't explain what they observed. Galaxies race through clusters at tremendous speeds. Those speeds require enormous gravity to keep galaxies bound. The hot gas sits in gravitational wells. Supporting that gas against gravity's pull requires massive amounts of matter. Add up all the visible material, stars and gas combined. It accounts for only a fraction of the gravity needed. Something else had to be there. This became known as the mass discrepancy problem. Observations required far more mass than anyone could see. The missing matter had to be dark. Not dark like a shadow, completely invisible, not interacting with light at all. The discrepancy is huge. Visible matter makes up roughly 20% of the total mass. The remaining 80% is something we can't detect directly. This invisible component dominates galaxy clusters completely. Without it, the entire structure would fly apart. Light travels in straight lines through flat space. But space around massive objects isn't flat. Mass curves space itself. When light from distant galaxies passes through a galaxy cluster, it follows those curves. The cluster's gravity bends the light's path. This creates distorted images of background galaxies. Astronomers call this gravitational lensing. Einstein's theory of general relativity predicted it. Galaxy clusters provide perfect natural laboratories for observing it. The amount of distortion directly measures total mass. More mass means stronger gravitational fields. Stronger fields bend light more dramatically. By measuring how much background galaxies get distorted, astronomers calculate the cluster's total mass. This method doesn't care whether mass is visible or dark. Gravity responds to all mass equally. Light bends based on total gravitational strength, regardless of what creates that gravity. Lensing measurements revealed something remarkable. The total mass far exceeds the visible matter. The measurements agree with other methods. Velocity measurements, gas distributions, all point to the same conclusion. Most of a cluster's mass is invisible. Dark matter doesn't spread evenly through galaxy clusters. It concentrates in a specific structure. Astronomers call this a dark matter halo. The halo extends far beyond the visible galaxies. Think of it as an enormous sphere of invisible material. The cluster's galaxies sit embedded within this sphere. The hot gas fills the spaces between galaxies. Everything lives inside the dark matter halo. This halo provides the gravitational framework. Dark matter fell together first, billions of years ago. Its gravity created deep potential wells. Normal matter then fell into those wells. The dark matter halo shaped where galaxies formed and how gas distributed itself. The halo's mass dwarfs everything else. For every bit of normal matter in a cluster, roughly 5 times more dark matter surrounds it. The dark matter halo is the real structure. The visible components are just tracers showing where the invisible mass sits. Mapping the halo requires indirect methods. Gravitational lensing traces its shape. Galaxy velocities reveal its depth. Gas temperature distributions show its gravitational pull. All these measurements combine to map something we can't see directly. The invisible becomes knowable through its gravitational effects. Dark matter doesn't distribute uniformly within its halo. Density varies with distance from the cluster center. This variation follows a specific mathematical pattern. Computer simulations predicted this pattern before observations confirmed it. The simulations showed dark matter halos naturally develop a characteristic density structure. Astronomers call this a Nefer-Wu profile, named after the researchers who first described it. The profile has 2 key features. Near the center, density rises sharply. This creates what's called a cuspy core, a central region where dark matter concentrates intensely. Moving outward from this core, density decreases following a power law. The farther you go, the more gradually density drops. This profile appears universal. Small dark matter halos show it. Massive galaxy cluster halos show it. The same basic shape appears across an enormous range of scales. Why does dark matter settle into this particular pattern? The answer comes from how halos form. Dark matter collapses gravitationally. The first material to collapse falls to the center. Later material settles at larger radii. This inside-out growth naturally produces the Nenfavu profile. The density structure encodes the halo's formation history. Galaxy clusters don't have sharp edges. They fade gradually into surrounding space. But astronomers define a useful boundary. They call it the virial radius. The virial radius marks where a cluster transitions from bound to unbound. Inside this radius, material belongs to the cluster. Gravity holds it in place. Outside this radius, material participates more in cosmic expansion than cluster dynamics. The definition comes from comparing densities. At the virial radius, the average density inside equals roughly 200 times the universe's average density. This specific value comes from theoretical calculations about gravitational collapse. Think of it as a practical definition of cluster size. The virial radius tells you where the cluster's influence effectively ends. It separates cluster members from field galaxies passing nearby. Measuring the virial radius requires knowing the mass distribution. That typically comes from combining multiple observations. Galaxy velocities extend to certain distances. Lensing measurements reach specific radii. The hot gas shows pressure support out to particular bounds. Where these measurements indicate density has dropped to the critical value, that's approximately the virial radius. Galaxies within a cluster don't sit still. They orbit through the dark matter halo. Their motion follows the same physics as planets orbiting a star. Each galaxy traces an elliptical path through the gravitational potential. Some orbits are nearly circular. Others are highly elongated. The orbits intersect and cross in complex patterns. As galaxies move through the dark matter halo, they experience drag, not from colliding with dark matter particles. Those interactions are too weak. The drag comes from gravitational interactions. The galaxy's gravity pulls on surrounding dark matter. That pull slightly redistributes the dark matter distribution. Astronomers call this dynamical friction. It acts like a brake on galaxy motion. Galaxies gradually lose orbital energy. They spiral slowly inward toward the cluster center. Dynamical friction affects larger galaxies more than smaller ones. Massive galaxies experience stronger drag. Smaller satellite galaxies are less affected. Over billions of years, many satellites spiral into the cluster core. The central dominant galaxy grows by absorbing these fallen satellites. The dark matter halo shapes orbital evolution through this friction process. Galaxy clusters contain a hidden complexity. Each member galaxy carries its own dark matter halo. These smaller halos sit embedded within the cluster's larger halo. Astronomers call the smaller structures subhalos. They represent dark matter that remained bound to individual galaxies despite the cluster's powerful gravity. Each galaxy arrived at the cluster surrounded by its own dark matter envelope. The cluster's tidal forces work to strip these subhalos. As a galaxy orbits through the cluster, differential gravitational pull tears at its dark matter. Material from the galaxy's outer dark matter halo gets pulled away. What remains is a smaller, denser subhalo tightly bound to the galaxy. Computer simulations reveal incredibly complex structure. Thousands of subhalos orbit within a single cluster halo. These subhalos range enormously in mass. Some contain entire galaxies. Others are dark matter clumps with no stars at all. This creates a hierarchy. The main cluster halo is the largest structure. Within it orbit galaxy-sized subhalos. Some of those might contain their own smaller sub-subhalos. The entire structure resembles nested Russian dolls. Each level of hierarchy formed through gravitational collapse at different epochs. The nested halos record the cluster's entire assembly history. A galaxy entering a cluster carries dark matter with it. That dark matter won't all survive the journey. Tidal forces will strip much of it away. Tidal forces arise from gravity gradients. The cluster's gravity pulls harder on the galaxy's near side than its far side. This differential pull stretches the galaxy. Material loosely bound to the galaxy gets torn away. Dark matter on the galaxy's outskirts is most vulnerable. It orbits the galaxy relatively slowly. Weak binding means the cluster's tidal forces can overcome the galaxy's gravity. The outer dark matter halo gets peeled away like layers of an onion. What remains is a truncated halo. The galaxy keeps only its innermost, most tightly bound dark matter. Simulations show galaxies can lose more than half their original dark matter through tidal stripping. Some lose even more. The stripped dark matter doesn't disappear. It joins the cluster's main dark matter halo. Tidal stripping transfers mass from subhalos to the primary halo. Over billions of years, this process smooths out the cluster's dark matter distribution. The cluster halo grows partially by cannibalizing the halos of its member galaxies. Scientists don't know what dark matter actually is. They know it exists. They can measure its gravitational effects precisely, but they haven't identified the particle that makes it up. The leading candidate is something called a WMP. That stands for weakly interacting massive particle. These hypothetical particles would have mass but barely interact with ordinary matter. They would pass through normal material almost like ghosts. WMPs would interact through gravity and possibly the weak nuclear force, not through electromagnetism. That's why they don't emit, absorb, or reflect light. They're genuinely dark. Despite decades of searching, no one has detected WMPs directly. Experiments deep underground look for rare collisions between WMPs and atomic nuclei. Particle accelerators try to create WMPs in high-energy collisions. Space telescopes search for radiation from WMP annihilations. So far nothing. The searches continue getting more sensitive. But WMPs remain hypothetical. Other candidates exist. Actions are lighter particles that could make up dark matter. Primordial black holes formed in the early universe might contribute. Some theories suggest modifications to gravity rather than new particles. The dark matter mystery remains unsolved. We see its effects everywhere but can't catch the particles responsible. Astronomers can simulate cosmic structure formation on computers. They input the laws of physics and initial conditions. The simulation evolves forward in time, showing how structure grows. These simulations produce galaxy clusters. The simulated clusters show realistic properties. Their masses, sizes, and internal structure match observations remarkably well. The simulations make specific predictions. They calculate how many clusters should exist at different masses. They predict how cluster abundance changes with cosmic time. They forecast how dark matter distributes within clusters. Observations confirm these predictions. Astronomers count real clusters and measure their masses. The observed mass function, how many clusters exist at each mass, matches simulation predictions. This agreement extends across cosmic history. This success validates our understanding. The simulations assume dark matter dominates cosmic structure. They use relatively simple physics for how dark matter behaves. The fact that simulated clusters match reality so well suggests those assumptions are correct. The simulations also reveal details observations can't easily access. They show how individual dark matter particles move. They track how halos merge and grow. They predict structure on scales too small to observe directly. Computer simulations provide a window into the invisible universe. Dark matter and galaxies don't trace each other perfectly. Galaxies concentrate more strongly than dark matter does. This creates what astronomers call galaxy bias. Think of dark matter as the background framework. It smoothly fills the universe with gentle density variations. Galaxies form in the highest density peaks. They don't form everywhere dark matter exists. Only special locations birth galaxies. This creates a bias. Measure the clustering of galaxies. Then measure the clustering of dark matter through gravitational effects. Galaxies cluster more tightly. The galaxy distribution is biased compared to the dark matter distribution. The bias factor quantifies this difference. A bias factor of 2 means galaxies cluster twice as strongly as dark matter. Different types of galaxies show different bias values. Massive galaxies in rich clusters show higher bias. Small galaxies in sparse regions show lower bias. Understanding this bias reveals galaxy formation physics. Why do galaxies form preferentially in certain dark matter halos? What determines which halos host galaxies and which remain dark? The bias encodes answers to these questions. In galaxy clusters, the bias manifests clearly. Galaxies can concentrate toward cluster centers more strongly than dark matter does. The galaxy distribution can become more centrally concentrated than the underlying dark matter through dynamical friction and mergers. 2 massive galaxy clusters collided billions of years ago. Astronomers call the result the bullet cluster. What they observed there changed everything. The collisions separated different types of matter, hot gas in one location, dark matter in another. For the first time, astronomers could map dark matter and normal matter in different places. Here's what happened. Each cluster contained galaxies, hot gas, and dark matter. When they collided, these components behaved differently. The galaxies mostly passed through each other. Space is mostly empty. The hot gas clouds from each cluster crashed together violently. But the dark matter did something remarkable. It passed straight through without interacting much. The 2 dark matter halos slid past each other like ghosts. They ended up ahead of the gas clouds, still traveling with their galaxies. Gravitational lensing revealed this separation. Background galaxies showed strong distortion. Mapping that distortion revealed where the mass sits. Most of the mass sat with the galaxies and dark matter. The hot gas, visible in X-rays, lagged behind in between. This provided direct evidence that dark matter does not interact with itself strongly. If dark matter particles collided like gas does, the dark matter would have stayed with the gas. Instead, it passed through cleanly. The bullet cluster became one of the most compelling pieces of evidence that dark matter exists as weakly interacting matter. Galaxy clusters do not drift together slowly. They approach each other at staggering speeds, thousands of kilometers per second. Gravity accelerates the clusters toward each other. Over hundreds of millions of years, they fall together through cosmic expansion. By the time they meet, they are moving at incredible velocities. These speeds carry enormous kinetic energy. Think of 2 mountains racing toward each other faster than bullets. The energy involved dwarfs anything we experience on human scales. When structures this massive collide at these speeds, the results are spectacular. The kinetic energy has to go somewhere. Much of it converts to heat. The gas heats to tens of millions of degrees, hotter than most stellar cores. The collision velocity determines the merger's violence. Faster collisions create more dramatic effects. Stronger shock waves, higher temperatures, more turbulence. The velocity essentially sets the energy budget for everything that follows. 2 clusters colliding at several thousand kilometers per second release more energy than billions of supernovae combined. The hot gas between galaxies travels at tremendous speed during a merger. It moves faster than sound waves can travel through that gas. This creates a crucial condition. When gas moves faster than its own sound speed, shock waves form. Think of a sonic boom from a supersonic jet. The same physics applies on cosmic scales. The leading edge of one cluster's gas plows into the other cluster's gas. Material cannot get out of the way fast enough. It piles up suddenly. This creates a sharp boundary, a shock front. Crossing the shock front changes everything. The gas suddenly compresses, its density jumps, temperature spikes dramatically. The smooth supersonic flow becomes hot, turbulent chaos. These shock fronts are not subtle. X-ray observations reveal them as sharp brightness edges. The temperature and density jumps are measurable. Some shocks are strong enough to heat gas to over 100 million degrees. The shock front represents where kinetic energy converts to thermal energy. Gas moving at thousands of kilometers per second hits the shock and essentially slams on the brakes. All that kinetic energy transforms into heat. The shock front is the merger's most violent interface. Individual galaxies within merging clusters face a hostile environment. They are not just orbiting peacefully anymore. They are plowing through hot gas at enormous speeds. This creates ram pressure. Picture sticking your hand out a car window. The air pushes against it. Galaxies experience the same effect. As they move through the intracluster medium, the hot gas pushes back. This pressure is strong enough to strip gas from galaxies. Each galaxy contains its own gas reservoir. That gas is relatively cool and loosely bound. The ram pressure overcomes the galaxy's gravity and blows the gas away. Observations show long tails of gas streaming behind galaxies. These tails point directly away from the galaxy's motion. The stripped gas gets left behind in the cluster medium. Losing this gas has profound consequences. Galaxies need gas to form new stars. Strip away the gas and star formation stops. The galaxy becomes red and dead, full of old stars with no new ones forming. Cluster mergers dramatically accelerate this stripping process. The gas density increases. Galaxies move faster through the disturbed medium. Ram pressure intensifies. Many galaxies lose most of their gas during a single merger event. Dark matter behaves completely differently than gas during cluster mergers. Gas collides violently. Shock waves form, temperature spikes. The gas knows it hit something. Dark matter does not notice the collision at all. Dark matter particles apparently do not interact with each other in any significant way. They respond to gravity. That is it. No electromagnetic forces. No strong nuclear forces. Essentially no collisions. When two dark matter halos meet, the particles just pass through each other. Imagine two swarms of insects flying through each other. Each particle follows its gravitational trajectory, unaffected by other dark matter particles nearby. This creates the separation observed in the bullet cluster. The dark matter halos passed through the collision zone. The gas got stuck there. The galaxies, mostly empty space themselves, passed through with the dark matter. This collisionless behavior reveals dark matter's fundamental nature. Whatever particle makes up dark matter, it interacts incredibly weakly with itself. This property shaped how dark matter halos formed throughout cosmic history. Without collisions to dissipate energy, dark matter cannot collapse the way gas does. It forms smooth, extended halos rather than concentrated structures. During cluster mergers, galaxies experience complex gravitational interactions. Most galaxies eventually settle into stable orbits, but some get ejected entirely. This happens through gravitational encounters. Imagine two galaxies passing close together. Their mutual gravity deflects both trajectories. Usually the changes are small, but sometimes the encounter is violent enough to fundamentally alter a galaxy's orbit. Three-body interactions create the most dramatic effects. A galaxy passes near a binary system. Two massive galaxies orbiting each other. The complex gravitational dance can fling the passing galaxy outward at high speed. If the velocity boost is large enough, the galaxy exceeds escape velocity. It leaves the cluster entirely. Astronomers observe isolated galaxies in voids between clusters. Many likely originated as ejected cluster members. The process also works in reverse. Galaxies can lose energy and spiral inward. The net result is that mergers redistribute galaxy orbits. Some sink toward the center. Others get kicked to larger radii. A few escape completely. These interactions are most common during the chaotic phases of cluster mergers. When two clusters first collide, the gravitational field becomes highly time variable. Galaxies experience rapidly changing forces. This dynamic environment creates opportunities for dramatic orbital changes. Cluster mergers release staggering amounts of energy. That energy does not just disappear. Most of it goes into heating the gas. The temperature increase is dramatic and measurable. Before a merger, Cluster gas typically sits at tens of millions of degrees. After the merger, temperatures can double. Some shock-heated regions reach over 100 million degrees. This heating directly affects X-ray emission. Hotter gas emits more X-rays. The relationship is not linear. It is strongly temperature dependent. Double the temperature, and X-ray brightness can increase by much more than a factor of 2. Observations confirm this effect. Merging clusters appear brighter in X-rays than relaxed clusters of similar mass. The merger energy temporarily boosts their X-ray luminosity. The temperature increase also affects the cluster's long-term evolution. Hot gas takes longer to cool. The merger effectively resets the cooling clock. Processes like star formation in the central galaxy get disrupted. The cluster will not settle back into equilibrium for billions of years. Tracing temperature distributions reveals merger history. Smooth, symmetric temperature profiles indicate relaxed clusters. Complex patterns with multiple temperature peaks signal recent or ongoing mergers. The temperature map records the violence of cluster collisions. Relaxed galaxy clusters show beautiful symmetry. Their shape approaches a sphere. Galaxies distribute smoothly. Gas density decreases gradually outward. Everything looks ordered. Cluster mergers destroy this symmetry completely. The collision creates complex, asymmetric structures. Multiple density peaks appear where cluster cores overlap. The gas distribution becomes irregular. Galaxies cluster in unexpected patterns. The once spherical shape becomes elongated or fragmented. This morphological disturbance is visible in multiple ways. X-ray images show irregular brightness patterns. Galaxy distributions appear clumpy rather than smooth. Gravitational lensing maps reveal elongated mass distributions. The disturbance evolves over time. Immediately after collision, the morphology is most chaotic. Separate cores are clearly visible. The structure looks like two clusters overlapping. As time passes, the cores begin to merge. The morphology gradually becomes more regular. Astronomers classify clusters by morphology. Relaxed clusters have smooth, symmetric appearances. Disturbed clusters show irregular features. The morphology directly indicates recent merger activity. Completely relaxed morphology requires billions of years without major mergers. The shape tells the cluster's dynamical story. Cluster mergers create features invisible to optical telescopes. These structures only appear at radio wavelengths. Astronomers call them radio relics. Radio relics form at shock fronts. Remember those shocks created by supersonic gas collisions? They do not just heat gas. They also accelerate particles. Some electrons get boosted to nearly light speed. These relativistic electrons spiral around magnetic field lines. This motion generates radio waves through a process called synchrotron radiation. The result is a glowing arc of radio emission. These relics often appear at cluster outskirts, marking where shock waves traveled through the gas. They trace the merger's geometry, the direction and speed of the collision. Radio relics can extend for millions of light years. They are enormous by any standard, yet they are completely invisible except at radio wavelengths. They emit no X-rays, no visible light, nothing but radio waves. The radio emission eventually fades. The relativistic electrons lose energy over time. Within hundreds of millions of years, the radio relics disappear. They mark recent merger activity. Cosmic fossils of violent collisions. After the initial collision, the merger is not over. The clusters have passed through each other, but they remain gravitationally bound. They will fall back together. This begins a long relaxation process. The clusters oscillate back and forth several times. Each passage through the system dissipates energy. Gas friction and shock heating convert kinetic energy to heat. Eventually, the oscillations dampen. The separate cores merge into one. The gas settles into a new equilibrium. The morphology becomes more symmetric. Temperature gradients smooth out. This relaxation takes time. Billions of years, typically. The exact duration depends on the merger parameters. More equal mass mergers take longer to relax. Head-on collisions settle faster than glancing impacts. Astronomers observe clusters at various relaxation stages. Some show two distinct cores. Others appear partially merged. Fully relaxed clusters show no signs of recent mergers. The final state is a larger, more massive cluster. It contains all the material from both progenitors. The merger permanently altered its properties. The new cluster has different temperature, different mass, and different structure than either parent. Mergers represent the primary mechanism for cluster growth throughout cosmic history. Galaxy cluster mergers were not equally common throughout cosmic history. The merger rate changed dramatically as the universe aged. In the early universe, structures were just forming. Small galaxy groups merged frequently, but massive cluster mergers were rare. The first large clusters were still assembling. Peak merger activity occurred several billion years ago. This was the epoch when most galaxy clusters formed. Multiple groups came together rapidly. The merger rate reached its maximum. Since then, the merger rate has declined. Cosmic expansion accelerated due to dark energy. This expansion fights against gravity. Structure formation slowed. Major cluster mergers became increasingly rare. Today's universe contains many relaxed clusters. They completed their assembly long ago. Ongoing major mergers are relatively uncommon. We observe them, but they represent special cases rather than the norm. This evolution reflects the hierarchical growth of structure. Small structures formed first and merged to build larger ones. The merger rate tracks this bottom-up assembly. Early rapid merging gave way to a quieter modern era. The changing merger rate records the universe's structural history from chaos to relative calm. A galaxy entering a rich cluster faces immediate danger. The space between cluster galaxies isn't empty. It's filled with hot plasma. That plasma creates a problem. The galaxy is moving fast, thousands of kilometers per second through the cluster. As it plows through the hot gas, resistance builds. The intracluster medium pushes back against the galaxy's motion. This creates ram pressure. The term comes from the force you feel when moving through a fluid. Hold your hand out a car window. The air pushes against it. Galaxies experience the same physics on cosmic scales. The pressure is strong enough to strip gas from the galaxy. Each galaxy contains its own reservoir of cool gas. That gas fuels star formation, but it's only loosely bound to the galaxy by gravity. Ram pressure overcomes that weak binding. The hot intracluster medium blows the cool gas away. Observations show long tails of stripped gas trailing behind galaxies. These tails can extend for hundreds of thousands of light years. The stripping happens quickly. A galaxy can lose most of its gas in a single pass through the cluster core. Once the gas is gone, star formation stops. The galaxy's fate is sealed by this cosmic headwind. Massive galaxies in clusters don't just orbit independently. They pass close to each other, sometimes very close. When they do, gravity creates distortion. The effect comes from tidal forces. These forces arise because gravity weakens with distance. One side of a galaxy feels stronger pull than the other side. This differential pull stretches the galaxy. Think of ocean tides on Earth. The moon's gravity pulls harder on the near side than the far side. This creates tidal bulges. Galaxies experience the same effect when they pass near each other. Small galaxies suffer most. A small galaxy passing near a massive one gets stretched dramatically. Stars on the near side accelerate toward the massive galaxy. Stars on the far side lag behind. The galaxy elongates. Repeated close passes compound the damage. Each encounter stretches the galaxy further. Its original shape distorts. Stars get pulled into long streams. The galaxy's structure fundamentally changes. These tidal interactions are common in dense cluster cores. Galaxies there experience frequent close encounters. Over billions of years, tidal forces reshape many cluster galaxies from their original forms. Star formation requires gas. Without gas, no new stars can form. Galaxy clusters excel at removing gas from their members. The term astronomers use is quenching. It means shutting down star formation. Cluster environments quench galaxies efficiently through multiple mechanisms working together. Ram pressure strips gas away. Tidal interactions can disrupt gas clouds. The hot intracluster medium prevents galaxies from accruing new gas from outside. Cut off from both internal reserves and external supply, galaxies run out of fuel. The transformation is dramatic. A galaxy entering the cluster might be forming stars actively. Its spiral arms glow with young blue stars. Gas clouds throughout its disk birth new stellar generations. Within a billion years, that same galaxy looks completely different. Star formation has ceased. The blue stars have aged and died. Only old red stars remain. The galaxy appears red and dead. Astronomers observe this effect statistically. Measure star formation rates in field galaxies outside clusters. Then measure rates in cluster galaxies. Cluster members show dramatically suppressed star formation. The dense environment quenches galaxies systematically. Galaxies come in distinct types. Spiral galaxies have beautiful rotating disks with elegant arms. Elliptical galaxies appear as smooth, egg-shaped collections of stars with no disk structure. Cluster environments favor one type over the other. Count galaxy types in clusters versus the field. Clusters contain far more elliptical galaxies. Spirals are relatively rare in dense cluster cores. This wasn't always true. Look at clusters in the early universe. They contained more spirals. The spiral fraction has decreased over cosmic time. Something transforms spirals into ellipticals. Several processes contribute. Major mergers between galaxies can destroy disks and create elliptical structures. Repeated tidal encounters puff up disks, thickening them into spheroids. Gas stripping plays a role too. Remove the gas from a spiral galaxy. Star formation stops. The thin disk gradually thickens through gravitational interactions. The spiral arms fade. Given enough time, the galaxy resembles an elliptical. There's also an intermediate stage. Astronomers call them S0 galaxies or lenticular galaxies. They have a disk-like spirals but no spiral arms. Many cluster galaxies show this transitional morphology. They're spirals that lost their gas and evolved partway toward elliptical structure. Galaxies in cluster cores don't collide directly very often. Space is too big, but they do pass near each other frequently. Each passage creates a small gravitational disturbance. Individually, these encounters are weak. A single close passage might barely affect a galaxy, but they happen repeatedly, dozens or hundreds of times over billions of years. Astronomers call this harassment. It's the cumulative effect of many weak encounters. No single interaction destroys the galaxy, but the repeated harassment adds up. Each passage heats the galaxy's stars. By heating, astronomers mean increasing their random velocities. Stars start moving faster in random directions rather than orderly rotation. The galaxy's velocity dispersion increases. This process particularly affects disk galaxies. Disks are dynamically cold. Stars move in ordered circular orbits. Harassment heats the disk. Stars gain velocity perpendicular to the disk plane. The disk thickens. Over time, harassment can completely destroy a thin disk. What remains is a thicker, puffier structure. The galaxy transforms from a flat spiral into something resembling elliptical. Harassment serves as a slow but steady evolutionary pressure in dense environments. At the center of most rich clusters sits one dominant galaxy. This central giant didn't start out so massive. It grew by eating smaller galaxies. The process is called galactic cannibalism. The central galaxy consumes other cluster members that venture too close. This isn't a collision between equals. It's a complete absorption. Small galaxies spiraling into the cluster center get tidally disrupted. Their stars get spread out into long streams. Those streams eventually merge with the central galaxy. The victim galaxy disappears completely. This process has been operating for billions of years. Each absorbed galaxy adds its stars to the central galaxy's mass. Hundreds or thousands of small galaxies have fallen in over the cluster's lifetime. The result is a supergent elliptical galaxy. These central dominant galaxies are among the most massive galaxies in the universe. They can contain trillions of stars, far more than the Milky Way. Evidence of cannibalism appears in the central galaxy's structure. Faint shells and streamers surround many of them. These features are the remnants of disrupted galaxies, stellar streams in the process of being absorbed. The central galaxy's halo is built from the corpses of its victims. Plot galaxy colors against their brightness. Field galaxies show a scattered distribution, but cluster galaxies reveal a tight pattern. Brighter cluster galaxies are systematically redder. Fainter ones span a wider color range. This creates what astronomers call the red sequence, a narrow band in the color brightness diagram where most bright cluster galaxies sit. The red color indicates old stellar populations. These galaxies contain stars formed billions of years ago. They lack young blue stars. Star formation ceased long ago. The tight correlation reveals environmental processing. Cluster galaxies evolved differently than field galaxies. The cluster environment systematically transformed them. Gas stripping, harassment, and other processes created this uniform population of red galaxies. The red sequence becomes more prominent in richer clusters. Dense environments more efficiently quench star formation. The tighter the red sequence, the more processed the galaxy population. Some cluster galaxies lie off the red sequence, the bluer indicating ongoing star formation. These are typically recent arrivals to the cluster. They haven't yet experienced the full environmental effects. Give them time, and most will evolve onto the red sequence. The color-brightness relation maps galaxies' environmental histories. Most massive galaxies contain supermassive black holes at their centers. In cluster central galaxies, these black holes play a crucial role. They regulate gas cooling and star formation. The black holes don't just sit there. They actively feed on surrounding gas. As material spirals inward, it heats to extreme temperatures. This creates what astronomers call an active galactic nucleus, an AGN. The AGN releases enormous energy. Some of this energy emerges as jets, beams of energetic particles shooting outward at nearly light speed. These jets plow into the surrounding hot gas. The jets inflate bubbles in the intracluster medium. These bubbles are visible as cavities in X-ray images. Dark regions where the hot gas has been pushed aside. The bubbles rise outward from the galaxy center like hot air balloons. This process heats the surrounding gas. The heating counteracts cooling. Remember that gas in cluster cores should cool and fall inward. Without heating, that cooling would trigger massive star formation. The AGN prevents this. It provides just enough heat to balance the cooling. Too much heating would blow all the gas away. Too little and cooling wins. The system self-regulates. A feedback loop between cooling gas and black hole activity maintains equilibrium. Galaxies evolve by consuming their gas. Star formation converts gas into stars. Over time, gas reservoirs deplete, but field galaxies can replenish their supply. Gas accretion from the cosmic web provides fresh fuel. Field galaxies sit in filaments of matter connecting cosmic structures. These filaments feed gas into galaxies continuously. Star formation can continue for billions of years. Cluster galaxies lose this supply line. The hot intracluster medium cuts them off. Gas trying to flow into a cluster galaxy from outside hits the hot cluster gas. The external gas gets shock heated and absorbed into the cluster medium. This creates gas starvation. The galaxy burns through its internal gas reserves. New gas can't reach it from outside. Eventually, the internal supply runs out. The evolution is one way. Once a galaxy joins a rich cluster, it's cut off from external accretion. It must survive on its existing gas alone. That gas gets steadily consumed through star formation and lost through stripping. This explains why cluster galaxies evolve faster than field galaxies. They're on a countdown clock. Limited fuel, no resupply. Star formation must eventually cease. The galaxy ages rapidly in the harsh cluster environment. Not all cluster regions create equal environmental effects. Location within the cluster matters enormously. The effects scale with local density. The cluster core represents the harshest environment. Galaxies pack most densely there. Ram pressure reaches its maximum. Encounter rates peak. Tidal forces are strongest. Environmental processes operate most efficiently. Moving outward from the core, conditions gradually ease. The intracluster medium becomes less dense. Ram pressure weakens. Galaxies spread out more. Encounter rates drop. Environmental effects become gentler. Observations confirm this gradient. Measure galaxy properties as a function of cluster-centric distance. Star formation rates increase moving outward. The fraction of spiral galaxies rises. Colors become bluer on average. The cluster outskirts resemble the field more than the core. Galaxies there experience intermediate conditions. They're beginning to feel environmental effects, but not the full force yet. This creates a radial processing gradient. Galaxies entering from outside first encounter mild effects at large radii. As they orbit inward, conditions intensify. Reaching the core means experiencing maximum environmental pressure. The cluster transforms galaxies from outside in. Look at galaxies currently in cluster cores. They appear remarkably robust. They survived the extreme environment. But this creates a misleading impression. We're seeing survivors. Galaxies that couldn't handle cluster conditions are already gone. They got destroyed, absorbed, or ejected. What remains is a biased sample. This is survival bias. We observe only the galaxies tough enough to survive. The failures left no trace. Countless small galaxies fell into cluster cores over billions of years. Most got tidally disrupted and absorbed. We never see them. This affects our understanding of galaxy evolution. Cluster galaxies appear adapted to harsh environments. That's partially true, but it's also that poorly adapted galaxies simply don't survive to be observed. The bias is strongest in old, relaxed clusters. These systems had billions of years to destroy weak galaxies. Only the toughest remain. Younger clusters retain more of their original population diversity. Simulations reveal what we can't observe directly. They track all galaxies, including those that get destroyed. The simulations show that cluster cores contained far more galaxies in the past. Many small galaxies contributed their stars to the central giant or got completely disrupted. The observed population represents survivors selected by billions of years of environmental processing. Point a telescope at a rich galaxy cluster. You'll see thousands of galaxies, but look more carefully. Strange curved features appear. Long bright arcs stretching across the image. These aren't cluster members. They're background galaxies far beyond the cluster. Their light passed through the cluster's gravitational field on its way to Earth. The gravity bent that light. This is gravitational lensing in action. Massive objects curve space itself. Light traveling through curved space follows curved paths. The result is distorted images of distant objects. The arcs can be enormous. Some span hundreds of thousands of light years in projected size. They appear much larger than the original galaxy. The cluster's gravity is magnifying and stretching the background galaxy's image. Einstein predicted this effect decades before anyone observed it. His general theory of relativity showed that mass bends spacetime. Light follows the curves in spacetime. Massive enough concentrations of matter should create visible distortions. Galaxy clusters provide the perfect conditions. Enormous mass concentrated in relatively small volumes. Background galaxies everywhere to serve as light sources. The geometry creates spectacular lensing displays. These gravitational telescopes reveal the universe's structure through warped space. What happens when a background galaxy sits perfectly behind a cluster? When the alignment is exact, something special occurs. The lensed image forms a complete circle. Astronomers call this an Einstein ring. It's named after Einstein's prediction of gravitational lensing. The ring represents the most symmetric possible lensing configuration. The ring's radius has significance. It depends on the cluster's mass and the distances involved. Astronomers call this specific radius the Einstein radius. It characterizes the cluster's lensing strength. More massive clusters have larger Einstein radii. The radius can also increase depending on the background galaxy's distance. These geometric factors determine the ring's size. Perfect Einstein rings are rare. They require precise alignment. The cluster center, the background galaxy, and Earth must line up exactly. Even small offsets break the symmetry. More commonly, astronomers observe partial arcs instead of complete rings. These represent near alignments. The background galaxy sits slightly off the perfect position. The result is a curved arc rather than a full circle. But measuring these arcs still reveals the Einstein radius and thus the cluster's lensing properties. Gravitational lensing doesn't just distort images, it amplifies light. The cluster's gravity focuses light from background sources. This creates a magnification effect. Think of a magnifying glass. It concentrates light into a smaller area, making things appear brighter. Galaxy clusters work similarly. They gather light from distant galaxies and focus it toward Earth. The magnification can be dramatic. Some background galaxies appear dozens of times brighter than they would without lensing. This allows astronomers to see objects otherwise too faint to detect. The amplification varies across the cluster. Regions of strongest lensing produce the highest magnification. Background galaxies positioned behind these regions receive maximum brightening. Move slightly off this optimal position, and magnification decreases. This effect serves as a natural telescope. Astronomers deliberately observe through galaxy clusters to study very distant, faint galaxies. The cluster magnifies these distant objects, bringing them within detection limits. Without cluster lensing, many faint, distant galaxies would remain invisible. The magnification allows astronomers to peer deeper into the early universe than their telescopes could otherwise reach. Nature provides these gravitational telescopes for free. Every distorted background galaxy provides information. Its shape and position reveal the cluster's gravitational field. Combine many distorted galaxies and you can map the cluster's mass distribution. The process works backward from observations. Start with the distorted images you observe. Calculate what gravitational field would produce those distortions. That field reveals where mass must be located. This technique works regardless of whether the mass is visible or dark. Lensing responds to total gravitational mass. It doesn't care if that mass is stars, gas, or dark matter. The method provides a direct mass measurement. The resulting maps show remarkable detail. Astronomers can trace how mass concentrates toward cluster centers. They can identify multiple mass clumps in merging clusters. The maps reveal substructure invisible through other methods. Comparing lensing mass maps to galaxy distribution shows dark matter's presence. The lensing reveals total mass. Galaxy counts show visible matter. The lensing mass always exceeds the visible matter substantially. The difference must be dark matter. Lensing provides one of the most direct ways to map dark matter distributions. Sometimes a single background galaxy produces multiple images. The cluster's gravity bends light rays along different paths. Each path creates a separate image. Observers see the same galaxy in several locations. The number of images depends on geometry and mass distribution. Typical configurations produce 2 or 4 images. Rare cases can create even more. Each image shows the same galaxy from roughly the same cosmic epoch. The images don't look identical. Each follows a different light path through the gravitational field. This creates different magnifications and distortions. One image might appear stretched into an arc. Another might appear more compact. Identifying which images belong to the same source galaxy requires detective work. Astronomers look for matching colors and spectra. The images should show identical features. Only their shapes and brightnesses differ. Multiple imaging proves the lensing affects reality. It's hard to imagine how else the same galaxy could appear multiple times. The effect directly demonstrates space curvature. Light genuinely follows different curved paths through the cluster's gravitational field. Geometry and gravity conspire to create these cosmic marriages. Light from multiple images of the same takes different paths. Those paths have different lengths. Light traveling farther takes longer to arrive. This creates a time delay between images. Light reaching one image arrives before light reaching another. The delay can range from days to years depending on the geometry. Astronomers can measure this delay for variable sources. Imagine the background galaxy contains a supernova. The explosion brightens suddenly. That brightness change reaches different images at different times. Observers see the supernova appear in one image first. Days or weeks later, it appears in another image. They're seeing the same event twice, separated in time. The light took different routes through curved space. This time delay provides unique information. Combined with other measurements, it reveals the distances involved. It constrains the expansion rate of the universe. The same supernova, observed multiple times with measured delays, becomes a cosmic ruler. The effect is subtle and requires patience. Astronomers must monitor lensed systems for months or years, but the payoff is valuable. Time delays provide an independent method for measuring cosmological parameters. Not all lensing creates dramatic arcs. Most lensing is weak. It produces small distortions difficult to see in individual galaxies, but statistical analysis reveals the signal. Weak lensing slightly stretches galaxy images. The stretching is only a few %. One galaxy shows random orientation, but thousands of background galaxies show a pattern. They align preferentially in directions determined by the foreground cluster's mass. Measuring this requires precision. Astronomers must determine galaxy shapes accurately. They look for systematic alignments that shouldn't occur randomly. The aligned pattern reveals the gravitational field's structure. Weak lensing extends mass mapping beyond cluster cores. Strong lensing only works in the densest regions. Weak lensing traces mass throughout the cluster and into the outskirts. It provides the most complete mass maps available. The technique is now standard practice. Every major cluster study includes weak lensing analysis. The method reveals dark matter halos extending far beyond visible galaxies. It shows how mass distributes on the largest scales. Weak lensing transformed invisible dark matter into mappable structure. Galaxy cluster lensing serves cosmology beyond mapping individual clusters. The statistics of cluster lensing constrains cosmic parameters. How many clusters produce strong lensing? How does this change with cosmic time? These questions probe dark matter and dark energy. The abundance of massive clusters depends on how fast structure grows. Growth rate depends on matter density and dark energy properties. Dark energy affects structure formation. It drives accelerated cosmic expansion. Acceleration fights against gravity. This slows down structure growth. Fewer massive clusters form in universes with strong dark energy. Lensing statistics measure this effect. Count how many clusters create strong lensing arcs at different epochs. Compare the early universe to the late universe. The evolution reveals how structure growth changed over time. Multiple independent methods point to the same conclusion. Dark energy exists and affects cosmic evolution. Cluster lensing provides one of the cleanest ways to measure these effects. The beautiful arcs we observe aren't just pretty pictures. They're probes of the universe's fundamental properties. The universe's most distant galaxies are incredibly faint. They formed when the universe was young. Their light has traveled for billions of years to reach us. That light gets stretched and dimmed by cosmic expansion. Detecting these faint, distant galaxies pushes telescope capabilities to the limit. Even the largest telescopes struggle, but cluster lensing helps. The magnification makes faint galaxies visible. Astronomers deliberately search behind massive clusters. They're looking for strongly magnified background galaxies. The magnification can boost brightness by factors of 10 or more. Galaxies too faint to detect directly become observable through the cluster's natural magnification. This technique revealed some of the earliest galaxies known. Objects from when the universe was less than 1 billion years old. Without cluster magnification, these galaxies would remain invisible. The clusters serve as gravitational telescopes extending our observational reach. The magnified galaxies show the early universe's properties. How big were young galaxies? What were their star formation rates? How did their chemical compositions differ from modern galaxies? Cluster lensing allows astronomers to study these distant systems in detail impossible otherwise. Converting observed distortions into mass distributions requires sophisticated modeling. Astronomers build mathematical models of the cluster's mass distribution. They predict what lensing effects that model would create. Then they compare predictions to observations. The process is iterative. If the model doesn't match observations, adjust the mass distribution. Try again. Repeat until the model accurately reproduces all observed features. The final model represents the best estimate of the cluster's true mass distribution. The modeling incorporates multiple constraints. Strong lensing features constrain the core mass distribution. Weak lensing constrains the outskirts. Galaxy velocities provide additional information. All these measurements must fit together consistently. Sophisticated software performs these calculations. The models can include thousands of parameters describing the mass distribution. Computers test countless configurations seeking the best fit. The results are detailed mass maps showing where matter concentrates. Different research groups model the same clusters independently. Their results generally agree, confirming the method's reliability. Lens modeling has become a precise science. The models reveal cluster properties with accuracy impossible just decades ago. Gravitational lensing tests general relativity. Einstein's theory predicts exactly how mass should bend light. Observing actual lensing tests whether those predictions are correct. So far, observations match Einstein's predictions precisely. The amount of bending matches theoretical calculations. The geometry of arcs follows predicted patterns. Multiple images appear where theory says they should. Alternative theories of gravity make different predictions. Some theories suggest gravity behaves differently on cosmic scales. These theories predict different lensing effects. Observations rule out many alternatives. The tests are getting more precise. Early observations confirm lensing occurs. Modern observations measure it quantitatively. The bending angle, the magnification, the time delays, all match general relativity within measurement uncertainties. This represents a triumph for Einstein's theory. It works on cosmic scales involving massive clusters. It works over billions of light years. The same equations that describe falling apples describe bending light around galaxy clusters. Gravitational lensing proves general relativity applies throughout the observable universe. The early universe wasn't perfectly smooth. Tiny variations in density existed, incredibly small differences from one region to another. These variations came from quantum fluctuations in the first fraction of a second after the Big Bang. The differences were minuscule, 1 part in 100,000. Some regions had slightly more matter than average, others had slightly less. Random variations across all of space. These tiny ripples would grow. Gravity amplified the differences over time. Denser regions pulled in more matter. They became even denser. Less dense regions lost matter to their surroundings. They became emptier. This process operated on all scales simultaneously. Small fluctuations grew into galaxies. Larger fluctuations grew into galaxy clusters. The largest fluctuations became superclusters. The entire cosmic web emerged from these initial tiny variations. Without those early density fluctuations, the universe would remain perfectly uniform. No structure would ever form. No galaxies, no clusters, no stars or planets. The quantum wrinkles in the infant universe seeded everything we observe today. Structure didn't form all at once. The universe assembled its architecture in stages. Small structures formed first. They merged to create larger structures. Those merged to form even larger ones. Astronomers call this hierarchical structure formation. It's a bottom-up process. Simple building blocks combine into more complex structures, like constructing a building from bricks. The sequence proceeded predictably. First, dark matter formed small halos. Then those halos merged into larger halos. Galaxy-sized structures appeared. Multiple galaxies gathered into groups. Groups merged into clusters. This process continues today. We observe it happening. Small galaxy groups fall together. They create larger clusters. Some clusters merge to form even more massive systems. The hierarchy keeps building. Computer simulations reproduce this growth. Start with initial density fluctuations. Let gravity evolve the system forward in time. The simulations naturally produce hierarchical structure. Small halos merge to make large ones. The pattern matches observations precisely. Dark matter responded to gravity before ordinary matter did. It collapsed earlier and faster. This created the scaffolding for all later structure. Dark matter doesn't interact electromagnetically. It can't radiate energy away. This property allowed it to collapse efficiently. Regions of slightly higher data density pulled in more dark matter. The density difference grew. These collapsing regions formed dark matter halos, invisible gravitational wells distributed throughout space. The halos appeared when the universe was still young, long before galaxies formed. The halos provided gravitational anchors. Later, ordinary matter fell into these pre-existing wells. The dark matter halos determined where galaxies would form, where groups would assemble, where clusters would eventually emerge. This sequence was crucial. Without dark matter collapsing first, structure formation would have taken much longer. Ordinary matter had other forces to contend with: pressure, radiation. These forces resisted collapse. Dark matter faced only gravity. It led the way, creating the framework ordinary matter would later fill. Ordinary matter fell into the dark matter halos. Gas from the cosmic web streamed inward. Gravity accelerated it to tremendous velocities. Then something violent happened. The infalling gas hit gas already in the halo. The collision created a shock wave. Gas crossing the shock front suddenly compressed and heated. Temperatures spiked to millions of degrees. This shock heating was inevitable. Gas can't fall into deep gravitational wells without heating up. The gravitational potential energy converts to thermal energy. The deeper the well, the hotter the gas becomes. This explains why galaxy clusters contain such hot gas today. That gas heated through shock heating during the cluster's formation. Matter falling in from large distances built up tremendous speed. The shock stopped that motion and converted kinetic energy to heat. The heating continues whenever new material falls in. Clusters still accreting matter show active shock fronts. Gas streaming in from filaments hits the cluster gas. New shocks heat the fresh material. The process that started billions of years ago still operates in growing clusters today. Not all gas stayed hot. Some managed to cool down. Cooling gas could collapse further. Eventually it became dense enough to form stars. This is how galaxies formed within the dark matter halos. The cooling happened fastest in smaller halos. Lower mass meant shallower gravitational wells. The shock heating was less severe. Gas could radiate energy and cool within reasonable timescales. As gas cooled, it condensed. Dense clouds formed. These clouds fragmented. The fragments collapsed under their own gravity. Nuclear fusion ignited. Stars were born. This process created the first galaxies. Small systems formed early in cosmic history. They contained the first stellar populations. These early galaxies were the seeds for everything that followed. Cooling remained crucial throughout galaxy formation. Only gas that could cool could make stars. Halos where gas stayed too hot remained dark. The balance between heating and cooling determined which halos would host galaxies and which would remain barren. Once galaxies formed, they didn't remain isolated. Gravity pulled them together. Groups of galaxies merged to form larger groups. Eventually, these became galaxy clusters. The merging process unfolded over billions of years. Small groups contained just a few galaxies initially. Gravity caused them to orbit each other. Sometimes two groups would approach and merge. The combined system was larger and more massive. This wasn't always violent. Some mergers proceeded relatively smoothly. The systems gradually blended together. Other mergers were dramatic. High-velocity collisions created chaos. The different outcomes depended on the group's relative velocities and impact angles. Each merger left its mark. The merged system showed disturbed structure temporarily. Over time, it relaxed to equilibrium, but the mass had increased. The system had grown through accretion. Repeating this process many times builds galaxy clusters. Dozens or hundreds of small groups merge over cosmic history. Each contributes its galaxies, gas, and dark matter. The final cluster represents the accumulated result of billions of years of mergers. Look at galaxy clusters at different distances. You're seeing different cosmic times. Distant clusters show us the past. Nearby clusters show recent epochs. The progression reveals how clusters evolved. Early universe clusters looked different. They contained more blue galaxies. Star formation was more active. The hot gas was less prevalent. Structures appeared less relaxed. Everything looked younger because it was younger. Over cosmic time, clusters matured. Star formation gradually declined. Galaxies became redder on average. The hot gas component grew more prominent. Structures settled into equilibrium. The evolution proceeded systematically. Astronomers measure this progression through redshift. Redshift indicates distance and look-back time. Higher redshift means earlier epochs. Comparing clusters across redshift reveals their evolution. The pattern is clear. Young clusters differ systematically from old ones. The differences show how cluster galaxies evolve, how gas heats and accumulates, how structures relax. Every cluster today passed through these same evolutionary stages. How many galaxy clusters exist at different masses? This distribution is called the mass function. It reveals fundamental information about structure formation. The mass function has a specific shape. Many low-mass clusters exist, fewer intermediate mass clusters. Very massive clusters are rare. The distribution follows a predictable mathematical form. This shape arises from the initial density fluctuations and how gravity amplified them. Stronger initial fluctuations were rarer. They produced rarer massive structures. Weaker fluctuations were common. They produced abundant smaller structures. Measuring the mass function constrains cosmology. The observed distribution must match theoretical predictions. Those predictions depend on matter density, dark energy, and other cosmic parameters. Matching observation to theory pins down those parameters. The mass function also evolves with time. The early universe contained fewer massive clusters. Over time, more formed through mergers. Tracking this evolution reveals how fast structure grew. Fast growth means one thing about dark energy. Slow growth means another. The mass function serves as a cosmological probe. Hot gas in galaxy clusters should cool over time. It radiates X-rays continuously. That radiation carries energy away. Logic suggests the gas should eventually cool down completely. But that doesn't happen quickly. The cooling process takes time. Astronomers calculate how long based on gas density and temperature. They call this the cooling time. For typical cluster gas, the cooling time exceeds the current age of the universe. The gas is cooling, but so slowly that it hasn't cooled significantly yet. It remains hot billions of years after formation. This explains why clusters still contain hot gas. If cooling times were short, the gas would have cooled long ago. It would have condensed and formed stars. But cooling times are long. The gas stays hot. Only in the densest central regions can cooling become significant. There, gas density is high enough for shorter cooling times. This creates cooling flows in cluster cores. But throughout most of the cluster volume, gas remains too diffused to cool efficiently. The long cooling timescale maintains the hot intracluster medium we observe. Galaxy clusters don't form randomly throughout space. They form preferentially in regions that were initially overdense. This creates a bias in their distribution. The bias means clusters trace dark matter imperfectly. They concentrate more strongly than dark matter does. If dark matter has a gentle density variation, clusters form only at the peaks. This creates stronger clustering in the cluster distribution. The bias evolves with time. Early in cosmic history, the bias was stronger. Clusters formed only in the most extreme overdensities. As the universe evolved, less extreme regions began forming clusters too. The bias decreased. Measuring this evolution reveals how structure formation progressed. Strong bias means picky formation conditions. Weak bias means more permissive conditions. The changing bias tracks how efficiently gravity assembled structures over time. This connects to the mass function. More massive clusters show stronger bias. They required more extreme initial conditions to form. Less massive clusters show weaker bias. They could form in more typical regions. The bias pattern encodes formation history across the cluster population. Galaxy clusters formed throughout cosmic history, but that formation is ending. The universe's accelerated expansion prevents new clusters from assembling. Dark energy drives this acceleration. It creates a repulsive effect on cosmic scales. This expansion fights against gravity. Structure formation requires gravity to pull matter together. Accelerated expansion works against this process. The consequence is straightforward. As expansion accelerates, fewer new clusters form. Existing clusters continue evolving. They can still accrete nearby material. But entirely new clusters assembling from separate groups becomes increasingly rare. Eventually, cluster formation will cease completely. The universe will contain a fixed population of clusters. Those clusters will slowly evaporate over trillions of years. Galaxies will drift apart. The clusters will dissolve. But that's the distant future. For now, we observe a universe still containing young clusters, still showing some ongoing formation, still evolving actively. We're witnessing the late stages of cluster assembly, the cosmic epoch when gravity's ability to build structure yields to dark energy's expansion. Future astronomers will see a universe where cluster formation is ancient history. Count the number of galaxy clusters at different masses. A simple task with profound implications. The count reveals the universe's fundamental composition. More clusters exist than pure chance would predict. Their abundance depends on how much matter the universe contains. More matter means more gravitational pull. Stronger gravity forms more clusters. The count also reveals how fast structure grows. Rapid growth produces many massive clusters early. Slow growth delays massive cluster formation. The observed distribution constrains the growth rate. Astronomers measure cluster abundance across cosmic time. They count clusters in the nearby universe. They count clusters billions of years ago. The evolution shows how structure formation proceeded. This measurement technique is remarkably precise. It does not depend on complicated physics. Just count objects and measure their masses. The simplicity makes the method robust. The cluster mass function has become one of cosmology's most powerful tools for measuring matter density and structure growth. Hot gas fills galaxy clusters. That gas sits in pressure equilibrium. Measuring the pressure distribution reveals the underlying gravitational field. The pressure profile has a characteristic shape. High pressure at the center, gradually decreasing pressure moving outward. This pattern appears universal across clusters of different masses. The profile connects visible matter to dark matter. Dark matter creates the gravitational well. Ordinary gas responds by distributing itself in that well. Pressure balances gravity at each radius. The gas pressure traces the dark matter distribution. This connection allows detailed comparisons. Measure the gas pressure profile. Calculate what dark matter distribution would produce that profile. Compare to direct dark matter measurements from lensing. The profiles should match. They do match. This agreement confirms our understanding of both components. The dark matter halo shapes gas distribution. The gas distribution reveals the halo's properties. Two completely different types of matter following the same underlying gravitational structure. Galaxy clusters show predictable relationships between properties. Mass relates to temperature. Temperature relates to X-ray brightness. These connections are called scaling laws. More massive clusters contain hotter gas. The relationship follows from gravity. Deeper gravitational wells heat in falling gas more. The temperature essentially measures the well's depth. That depth relates directly to total mass. Hot gas emits more X-rays. The emission rate depends strongly on temperature. It also depends on gas density. Combining these effects creates a relationship between mass and X-ray luminosity. Bright clusters are massive. Faint clusters are less massive. These scaling laws are not perfect. Real clusters show scatter around the ideal relationships. The scatter reveals cluster physics. Recent mergers disturb the relationships temporarily. Cooling flows affect central temperatures. The deviations from perfect scaling teach us about cluster evolution. The laws also evolve with cosmic time. Early clusters showed slightly different relationships than modern ones. This evolution constrains how cluster properties change throughout cosmic history. Scaling laws serve as both measuring tools and physics diagnostics. The universe is expanding. Measuring exactly how fast requires knowing distances accurately. Galaxy clusters can help constrain those distances. The method uses multiple observables. First, measure cluster properties that do not depend strongly on distance. Gas temperature from X-ray spectra, velocity dispersion from galaxy motions. These are intrinsic properties. Next, measure apparent properties that do depend on distance. X-ray brightness, angular size. These change with distance. Comparing intrinsic and apparent properties helps constrain the distance. This works because cluster physics is reasonably well understood. The relationship between mass, temperature, and size follows broad patterns. Knowing two properties can help estimate the third. If that estimated property disagrees with the observed value, the assumed distance may be wrong. The technique provides an independent line of evidence, independent from other methods like supernovae or Cepheid variables. Multiple independent methods strengthen confidence. When different techniques agree on the expansion rate, we trust the result more. Galaxy clusters contribute one useful piece to determining the Hubble constant, the number that describes cosmic expansion. Neutrinos are everywhere. Trillions pass through your body every second. These particles have mass. But how much mass? Galaxy clusters help answer that question. Neutrinos affected structure formation. In the early universe, neutrinos moved at nearly light speed. This free streaming prevented them from clumping. Regions smaller than a certain scale could not collapse if neutrinos dominated. The effect is subtle. Neutrinos make up only a tiny fraction of total matter, but even a small fraction affects structure. Heavier neutrinos suppress structure formation on certain scales more than lighter neutrinos. Galaxy clusters probe this effect. Their abundance depends on small-scale structure formation. Measure how many clusters formed. Compare to predictions with different neutrino masses. The observed abundance constrains possible masses. Current measurements set upper limits. Neutrinos cannot be too heavy or too few clusters would exist. The exact limit depends on other cosmic parameters, but galaxy cluster observations contribute crucial constraints. They help pin down the properties of the universe's most elusive common particles.